Good afternoon, YouTubers. We're going to continue working on this propeller and doing some analysis on it. I'm going to be doing a sort of a parametric study on it. I'm not sure what electric motor I will be using on this propeller, but the idea is to do some analysis about how many watts it consumes as you increase RPM. Let's say for example, from 1,000 RPM to about 10,000 RPM. What will be the watts that you can calculate? To know the watt, then you have to know the torque. And torque and RPM will help you to get the watts. So that's sort of the idea. So as always, when you do this type of study, we're going to be doing a flow simulation. You have to have a rotating box, a rotating part here that will cover my blades here, or my propeller in this case. So first of all, this is about, I think this is about between 10 and 11 inches, close to 11 inches, pretty much. What I'm gonna do is do that rotating part. So the best way to do the rotating part, let's say, for example, let's put this here and look like a top. You can do this box on the top side. So let's do sketch here. Before doing that sketch, let me change unit here. So I got inches, for example, and let's go back to top, sketch, and from here let's go to sketch here, pick a circle, and right at the center of this guy, there we go, and then start to make a circle. At the first, let's make it almost like touching the tip of the blade. That will give you 10.67, almost 11 inches, right? Between 10 and 11. We're gonna make it a little bit larger than that, more like this. All right, so that will do. So let's see where that is. That's right. You see, that's right at the middle, and that's good enough to me, because the next thing that we need to do is go features, extrude, and when we extrude here, we want to be sure that we are in the middle of it, mid plane, and that we can go both sides. I'm still in inches here, so let's give a few inches here and there so that it is well covered. You see there's a tip here at the top here that is still not yet covered, so increase it full inch. Let's see where we are. Can give you a little bit more, 1.5 maybe, 1.30. Let's give it 1.5. There we go. That's good enough. So we have our propeller covered in what is called by this concept of flow simulation as a rotating body. So we're gonna accept that. And never mind that you don't see the blade inside or the propeller. It doesn't matter. We will look for that when we complete the flow simulation. So now we jump to the flow simulation here, and what we have to do, go here and use the wizard. As simple as that. It's preparing the whole scenario for us. We're asking a few questions here and there. We call it project. I don't have any problem with that. Next. Now here, let's see where we are. The only thing that I might change a little bit, load and motion. Let's see where we are. Angular velocity, instead of being rad per second, you can leave it in rad per second, but I'd rather use RPM. And that's the only change that I will do. RPM. Anything else here that I want to change? Nope. Next. Now here, pick. It's gonna be external. Exclude anything of these, but then we're gonna have a rotating body. So that's the only thing that I would have to add to ensure that we analyze this propeller properly. Next, it's gonna be Air, no problem there. Next, next, no issue here. Look good. So now it's gonna take a little while, well, few seconds to get our project ready to go. So don't worry about this part. Depending on this, how fast your machine is, it's take a little while. I think mine is done now, and it come out with a huge computational domain. It's not a big deal. We go, if you leave this computational domain so big, it's gonna take a while depending of the mesh size that you use. So to begin with, I like to make it slightly smaller, perhaps, just so that the let's see where we are here. Let me get this in front and make it smaller now so I can see what I'm doing. Go back here and make it smaller. About once, if this is one side, just check that this is a slightly about the same. That's basically the idea. You can go by two sizes of these, perhaps. Not big deal. I just want to be sure that they start to look good. Smaller on this side. Yeah, more or less. That looks good for me. All right, now after adjusting the computational domain, let's see something here. Oh, I made a mistake. Let me fix that for you. And has to do with, let me do undo here. I think that I only have only one body here. I should have two. How we know that? Go back here quickly. Only one body. That's not good. So in other words, my last extrusion, I forgot to, let's show you what's the problem right here. Let's edit this. And no, no. Here's the problem. The problem is that I left the merge on. You have to have two bodies. One is for the propeller and the other one is for the rotating body. So check this out now. There we go. There's no, now I'm not gonna change anything. So I have the propeller and I also had then the rotating body. That was a problem. Let's go back now here. And now let's see. Right click, change transparency. There we go. Now you can see the propeller. Because it's good to see what's going on. Like for example, now the propeller needs to rotate counterclockwise. That's how this propeller is going to be done, meaning that the flow of air will go down and the propeller will want to go up. So that's the idea. So you know what's going on. All right, so good. Now that we are moving, go now to rotating region. Let's insert that. And here we are. The rotating region is that one. And it's going clockwise. I want counterclockwise, meaning that whatever number I put here, let's put minus 1,000. And let's see how this looks like. Yep. Now it's going counterclockwise, going that direction, and that makes sense. Now we are okay. If you get the negative out, for example, now it's going clockwise. Just leave the negative because we want that direction to be counterclockwise. So now it's counterclockwise and the air will be pushed down and the propeller want to go up. That's good. In the direction of the y positive. So the force has to be positive. The thrust has to be positive. So we accept that and we are starting with 1,000. I'm not yet doing the parametric study. I'm more like into, um, let's see what's going on here. Anything else look good? Now the next things, actually, let me check something here. Yeah, I can certainly do from here, but I want to run one just to be sure that everything looks good. And before doing any parametric study, I want to settle everything down. Boundary condition goals. Here we go. Let's insert some surface goal to start with. Those are going to be the force here, which is the one that I have a lot of interest. What is the thrust? But I also like to check on the normal force. So you do a calculation. They should be very similar almost to this value here to the force in y. All right, so I got that. Now since they are surface goal, I have to pick what the surface is going to be, and it's going to be this one, this one, this one, this one, this one, and this one. Yep, looking good. Got all the forces selected. All this, I'm sorry, I got all the faces selected for this bar, and anything else here? Nope, look good. So we accept that. Now the next thing is, let's get here. Let's add also a global goal, and as a global goal, I want the force in y, this direction. That will do as well. Now let me add here the definition. I want also hold it for a second here. No, let's go back here. Goal, insert surface goal. I want to add torque here. That will do as well. I need that value. And forgot I wanted all this. Should have done it when before, but it's all right. Accept that. So I got, let's see, as a goal, I got normal force, also surface goal in y, and global goals. So these three forces must be very close. And I also have the torque, which is important to measure watts. Looking good. Now let's insert an equation goal. And this equation goal will be, let's call it watt. Oops. Watt. And here, what we're gonna do is we're gonna pick torque. It's gonna be torque. We're gonna torque times, here's gonna be the rotate, whatever is the RPM from here, angular velocity, and that's gonna be that angular velocity. You have to be careful here. Right now, as you see, is minus 1,000 RPM, meaning that these gotta be fixed. You're multiplying torque, which has unit of Newton meters, time angular velocity, which are need to be radians per second. So meaning that I need to fix something here to get this right. So that will be multiplied by 2 times 3.14. Now, if I do that, I think that I will have watts in obviously unit of joules per second, which is what I want. So let's check this one again. This is RPM. might improve this. Hold for 1 second here. So the to have better resolution here, let's put 3.1416 here. 1/6, and that will do. So I think we got that. Now the unit here, last time I checked there was no unit for power, so no units, and we accept that. So we got all our equation that we need, I mean, which is what, and all the other forces. How about the mesh? Let's check on mesh, and let's see, create mesh. Well, actually, let me close it for a second before doing anything else. Edit definition. It's gonna be last time I like 5, looking good there, and we accept that. Now before doing anything, let's see where we are. Let's go 1 second here on flow simulation. On there's solve here, and let's see what we got. All goals, goal conversion, travel looks good, and one satisfied, no good. All satisfied, that's what you want. Be sure that you have that. Travel is the number of time that the system will go through your computational domain, and the more the better. It's just to ensure the numbers converge, and that's why I have more here, more calculation on the thrust, just to ensure that it is kind of a force to converge. If I see that this number is 1 and this is very far away, then I know that there's something weird going on. Now we're okay. So going back to here, edit definition, looks like I'm gonna leave that on 5. I don't see more of a problem there. All right, so that now what we can do is let's run this guy, create mesh, and now we set run. On your before doing any parametric study, your first run is to set the basis for that parametric run. It's sort of like a batch. We're going to be running kind of a batch type of flow simulations scheme here. So it's kind of popping on another window. Let me see if I can bring that window here so you can see it. So the mesh is done. Total number of cells and so forth, not a big deal here. That's where we are. Now, the next step is I don't see anything else to do except to run, because this is only the mesh is the only thing that has been loaded here. We are ready to run this flow simulation and run. The mesh is not connected. I mean, it's not punched here just because I like to run the mesh separately from this. So now we run, and now we go to a window here. There we go. And on this window, we're gonna pick what we want to plot. And I like to see that these 3 things kind of merge in one value, and maybe this one as well, so not to create too much stuff. And calculation will start shortly. They are going through now. And let's open this a little bit bigger. And we'll see. See, like you have negative value at the beginning. Those forces need to converge to a positive value at the end, because they are thrust, and thrust is going down, so the propeller want to go up. So forces must be positive. That will take a while, so we let that run for a little bit, and I'll be back. All right. So after a little bit more than, I don't know, about 30, 35 minutes or so, it complete the iteration, and here are the numbers. The forces pretty much close, the three of them, you see, about 0.29, 0.29, 0.292. They are very close. The torque is in the negative direction, no problem there. Counterclockwise, very small, it's about 1,000 RPM. And so it's done. And now we can start to check what's going on here, how this looks like at the end. How about if I disappear that, so I only have the propeller now? Because basically what I want to do is start to see, let's start with the flow trajectory. Let's insert that and let's take a look at it. Let's increase, I don't know, about 60 here. And instead of pressure, we're gonna get velocity, full velocity. Let's see right here. And so that would be these, and these. That will do. And anything else here? Look good. We accept that. And let's hide the computational domain so you see how this looks like. Not a big deal at 1,000 RPM. We are just starting this. But you can see strong blue here somewhere and there. And let's see what else we see here. Slightly with a better color here, getting into the 4 meters per second or so. Not a big deal at 1,000 RPM. Nothing that I can really say anything about it. But now, this is the part that is interesting. Let's go to project and project new parametric study. That's what we're gonna do. Then what we're gonna do here, we have a what if, goal, and design of experiment optimization. I'm gonna go with what if, and here we're gonna pick our first variable, and that's gonna be rotating body, rotating region. Here we're gonna go with angular velocity. We're gonna accept that. And let's see. We want to go for a range with step, and that's what we want. From -1,000 to, let's say, -10,000, and the step will be, I don't know, about 1,000. So that will do -1,000 to 10,000, and that we're gonna accept that. Oh, minimum cannot be greater than maximum. Let's see, that I'm missing something here. RPM. Oh, maybe this. Let's see. It's saying that this is the minimum because they are negative. And let's get this out. And now be careful here. Let's see the step. Will this work now? Let's see. -10,000 and 1,000. There we go. So you can see here, when I put the number right, it will go -10,000 and so forth up to 1,000. All right, so that will do. Now, what else I want to do here? I got the input variable, output parameters. Output parameters, let's see, goals. Here is all of them. I want all of them. So we accept that. And a scenario. Here are the scenarios that we are thinking that we're going to be running. And number of cores, let's see. Everything is in auto. I don't see anything else that I need to do here, and we'll see what happens. And let's put this so you can see this is more like a parametric study, but it's sort of like a batch study. I'm moving let's see if I can get this to show up. There we go. So that's the first run, and that's gonna be about 10,000 RPM, and we'll see what happens from there. See you later. All right, so after half an hour, I'm stopping by and checking what the number looks like. It seems like it complete the first scenario, about 10,000 RPMs, and the forces are huge, as expected. And let's see, watts. 2,000 watt. Even, I mean, humongous number for the RC plane. That's not possible on this scenario. I'm just, stressing the fact that I'm going to go from minus 10,000 to about 1,000. We already knows what this number looks like, but I'm entertaining the others as a parametric study with and the fact that what if the RPM is 10,000, what will be the number? And that will be done automatically, which is what the part that I really like about what I'm doing here on Solidworks on flow simulation, that all this can be done. While you're doing something else, you let the computer crunch all these numbers and you don't have to deal with it. I already did in a past video. I already did the other scenario like goal optimization. When you want a particular watt number, you are trying to target a particular watt number. Like last time was 150 watts for a type of electrical motor. And in this case, I'm not targeting any motor at all. I'm just calculating what would be the watts for this propeller at different RPMs if I operate at RPM, and what obviously the thrust force. So give you an idea how efficient is your propeller in general, your design. And I think this design is a lot better than the first one that I did on for the propeller. Oh well, we'll let this run for a while, and we'll come back. And because it's just starting, you and here in calculation, you don't see anything pretty much. We are going through the number 53. If I remember, for 1,000 was about 400 of these iterations before it converged to something. So we let it go, and we'll come back. All right, so here we are back again after 2 hours. Basically, we have the obviously the 10,000, the 9,000, the 8,000, and 7,000, and right now it's crunching the 6,000 RPM. And looking into the numbers, they look good. You see the forces. If I can turn this propeller at 10,000 RPM, that would not be possible, obviously, because the watts here are, let's see where the number is huge. 2,000 watt. That's not that doesn't make any sense. That's a lot. Uh, Remember that 1 horsepower is about 746 watts. So close to 3 and 4 horsepower. That's what you're talking about here. That's a huge number. Talking about RC type of propeller. So anyway, but it's just an estimate of what it will looks like. Now, about let's see where we are here. Let me get this a little bit higher so that I can see more into this. There we go. Like for example, at 9,000, it drops, the watt drops almost about half of what it was here, a little bit higher than 1,000. At 8,000, it's still a huge number. It's just almost a little bit higher than a full horsepower. This is at 7,000, it's just about 1 horsepower. That start to make more sense, but clearly is going to tell you that at the RC level that I'm working on, which is probably about no more than 300 watts, this got to go down on this propeller. But here are the forces in Newton. Let's see what else. Do we have to pay attention here? No, just let it go. It's about 2 hours already, so I expect to 1, 2, 3, 4, another 2 hours here, so that would be 4 hours, and about 1 hour here, so about 5 hours number crunching, and that will give me a good idea what this this propeller design will do, which is great. Because the idea here is not to fix it to any watt value, but more to get an idea what this propeller will do at different RPM, which is very nice. So, like for example, you have to force this propeller to have a certain thrust, then you know what you will be looking for the watts, you know, to have room to do that. All right, so we're gonna leave this number crunching for perhaps another hour and see what we have. Bye. All right, I'm back after about 5 hours number crunching. It went through all of them, 10 design points from minus 10,000 because it's turning, counterclockwise, and that's the negative where that comes from. And so basically, the most important parameter here that I was looking for was for the watts, which is a combination of the RPM and the torque as measured here. Remember that the torque needs to be, this torque is Newton meter, but the watts need that the RPM need to be changed to rad per second, radians per second. So, and that come out with this number here. So, as you can see, now is depending of what the force you are interested. Like for example, this is close to almost to 3,000 grams. Wow, that's a lot. 3,000 grams. And as you go down between numbers that will make more sense to me will be like a 6,000, still huge. 460, that's about half of a little bit more than half a horsepower. That's a lot in terms of electrical motor for an RC. So I would say the numbers, these 266 start to make more sense. So we're going to be somewhere here in this region. Like for example, if I use a motor that has a 150 watt limit, that means that probably will be an RPM between these two, between 4,000 and 5,000 and so forth. So that's the nice things about doing this fully automated in what is called a what if analysis, and that provide all this information. So the only thing that I have to do now is, if I want to do some graphics or some other stuff, let's save it for the time being, and we're going to save that information. As always, it's going to be a parametric study. Let's call parametric study for three-blade propeller. I can add more. Remember, this is based on I think it was a Sikorsky or something design for this blade, if I remember right. But anyway, parametric study for a three-blade propeller. We save it in flow simulation. That sounds good, and it's going to be saved. After that, you can copy this as well. You can copy everything and add that also to Excel, in case that you want to do something else at a later time. But it's also good to have everything, kind of in a secondary file just in case. But that's it. I think that this is everything that I have to say about it. And as always, thank you for watching. Have a great day. Bye. All right. I thought to finish the video before, but let me add this to this. Like for example, all right, you complete your study and everything. What happened next? Well, what happened is, let's say that I'm gonna open, perhaps let's open here so you see everything, and I'm gonna look for here, Win profile. That's the one that I was working on. Rep 4, open up. and now it will open at where I left it before, except that there's nothing loaded here. Remember, we cannot complete all the study here. In fact, we completed 10 study, and the point where they are. First of all, like for example, if you touch here and let's see, if we open this, it will open whatever it was saved at scenarios. Like for example, I save it here, save study as, but I never say the results. Not on here. So be careful where you save things at, because I wasn't interested to save this. Then okay, you might have saved it, but not in my case. I didn't. So that's why I want to be careful. What I gonna say to you, because basically the point is this: you save it here. Everything was saved here, but it's not loaded. I don't see anything here. Right? There's nothing there. But you did 10 studies. Where they are? Hit here and load from file. The important thing is that when you load, typically you want to save everything in a particular folder. It's called flow simulation, and I have a few things here and there, but it was saved with this weird name because it's part of this. It was part of analysis 1, so it cannot save it here. Now double click here and you can see many files where it went. Now this first study, it is not, because that's not the name. It was under a parametric study and it's right here. That's where you save it. You see, this one, it was for the the first study that I did at 1,000 RPM, but it's here on this parametric study is where you will get the others. Double click here and you can see the 10 files. Save it. Let's put one of them. Let's put number 5. Now we are here, study number 5. The file that you're looking is either an FLD or a CPTN. Now this file CPT is for the mesh. It's where they save the mesh. For I mean, the mesh is equal for all the runs that I did, no problem. Now this file, which has an R at the beginning, is for the first run, basically how you set up the solving your system. So that's not it either. So it is this one. This one is the one that has all the results that you are looking for. So that's the one that you want to open. The kind of weird name, right? That's the way it is. 5FLD. Open that one. So we double click here, or we just hit open, and it's gonna load the file. Now the file is loaded, and you can do the same for any of them, one by one, and you can look the details of each one. Now the question is, let's say for example that I have something here that is let's see, let's start by a cut plot. Insert, looking good there. From plane, contour, vector, that would be good. 10 to let's put like a 50 or so, and let's see what this will produce. Accept that, and here you have it. You can change, I mean, like for example, to improve this, I don't see any red here. You can double click here and change, like for example, instead of 87, get to, I don't know, maybe 70 here on the maximum. So just to improve 70, let's accept that, and you have it there. So you can see the air coming down this way, very little on the center at the hub. So that's an idea of checking how this looks like. That was on a cut plot. How about a surface plot? Let's see. Let's hide this one. We're gonna edit hide this one, and let's go to perhaps a surface plot. You can insert as well here, and let's pick for the surface plot all surface. That will do everything here. Again, I like contour and vector. velocity 50. We're gonna accept that, and here we have it. You can see the areas in where you will have a very high speed versus area that the speed will be very small, like on the blue here. But as you get to the tip of the blade, it's about 70 meters per second. That's a lot. And you see the behavior as well of the wind pattern on the blade. Interesting. All right. Now, you can change here anything that you want. Like for example, how about pressure? Right on the fly, and it would change you for pressure to indicate where is the high pressure zone versus the low pressure zone. Like for example, it's a high. This is kind of a yellowish color somewhere here above atmospheric pressure, and a little bit a bluish color here at the top of the blade, meaning that you're somewhere here below 1 atmosphere. So that's a vacuum right here. You have a vacuum here, sort of a pressure on this zone. Interesting as well. Good for designing a nice propeller that will do the job right with low torque but high velocity going down here. Now that was a surface plot. Let's get this high. How about iso surfaces? How about, I still have this one open here. Let me see. The definition, I have the 6 faces there. 60, I don't see a big deal here except to run it. And there we go. So you can see the behavior of the air near the propeller coming down and exiting kind of at a higher speed. You can see because of the green arrow here is somewhere in this zone versus the blue. The blue will be somewhere here around the blade. Now let's see, I like to do this on flow trajectories. Let's do a play so we see them, how they behave. So this, you can go the extra mile on designing your own blade by doing what I'm doing right now. It's looking good. So anything else? Let's stop this for a second. Let's hide this, and you can check the gold plot edit definition. I got all of them, and you can show them right here. They are right there, all of them, including watt. This is about 450, 458 watts. Not possible with the motor that I'm thinking to use, which is maximum 150, just to say the least. But it gives you an idea of what's going to happen. The forces are huge. I mean, it's about above 1,000 grams of forces here. That's what this estimate is. So you can take a look at all the numbers, how they looks like, and so forth. So we got that. Anything else here? Not really. We kind close this out. You can get the report. You can do that as well. I guess that's the main point. I mean, you can get a lot of information by moving through the 10 results that you put together on your parametric study. And what I'm gonna do now is do an Excel plot in where I check 3 blades versus 2 blades, the same size. It's just that I'm gonna analyze and see what perform better. Identical, except that the next propeller will be 2 blades. Still curious to see what will be the behavior of the 2 blades versus this one that has already been analyzed. Until then, have fun and thank you for watching. Bye.